Welcome everyone. We might start so we can start on good time and hopefully keep time with our sessions. Well, it makes my heart sing to see that urban water is given its own special mention at the NRM conference. It's both a suppressor and giver of life, and I'm sure that its potential to provide urban livability solutions and value is at least as in proportion to its ability to take it away or reduce our urban livability. So it's great to see. We'll get underway, and we've got Bree Bennett to join us here from the University of Adelaide, and she's going to talk about parsimonious simulation of daily rainfall fields. Welcome, Bree.
Good afternoon. This is a bit of a run-through of some work that's been done at the University of Adelaide in developing a model that can easily and flexibly simulate rain in both time and space. So, sorry. So why might we need such data? So typically when we're looking at a water system, we need some hydrological data to work with, whether that be rainfall or stream flow. So in my case, it's rainfall, and rainfall is really good where we have a catchment where potentially there's been some land use change or a change in the regulation flow. So we need our hydrological data to evaluate drought risk, flood risk, and ecological risks. And while it's very important to continue collecting historical observed data, there's really a limit to where it can take us because it's only one realisation of our climate. So we don't really get good estimates of risk from using our observed hydrological time series. So in the end, what we need is a stochastic source of data which gives us multiple realisations to put into our hydrological models to give us improved estimates of risk. So what is some stochastic hydrological data? So its most simplest explanation is that it's some random numbers that have been calibrated to have the same statistical properties and problems as our observed time series. But the good thing is we can generate many of these time series. So as each time series is an equally likely past climate past realisation that's equally likely to occur, we can actually use it as an input to our models to better quantify our uncertainty and get some probability limits. They have a variety of uses. Once we have our multiple realisations, we can use it to look at hydrological simulations, ecological simulations, whether you're trying to manage a water supply system in terms of storage and yield analysis, or our water resources. However, there's a further catch in that you can't just have multiple time series of data because our risks are correlated in space, whether it be drought or flood or ecological risk. So what we really need is spatial stochastic data. We need full evolving spatial fields of rainfall, in my case, to get good estimates of risk, further compounded by the fact that the spatial variability of the rainfall itself influences your catchment response. So with our spatial stochastic data, we can really get a better understanding of both our catchment processes and have better predictions of flood and drought risk. However, currently there's no easy, flexible approach to simulating these spatial rainfall fields, with current approaches poorly capturing spatial variability. Some rely on interpolation of observations, but we're back to that old problem of you only have one realisation and no time consideration. You might come across some multi-site rainfall models, but that's only part of the spatio-temporal relationship, only part of that spatial variability. And then we have some spatial models, but typically ones that are too complex and challenging to calibrate, to use, or perhaps they produce unrealistic spatial rainfall patterns, as for example the spatial Name and Scott model. So today I present to you a continuous daily rainfall field model that simulates the full rain field evolving in time, but using a parsimonious and flexible latent variable approach. Now, it's parsimonious because the amounts and the occurrences are simulated using one distribution, which also incorporates skewness. So we're not running two separate models, one that's doing rainfall occurrence and one that's simulating how much rainfall comes when it is wet. Other than this, you can have your rainfall fully distributed in space. You can choose the resolution, the spatial resolution of your rainfall, and you can have as many stochastic realizations as you would like. So a bit behind the model itself, the latent variable approach looks like this. So we have a distribution at each point in the grid made up of a mean, standard deviation, and a transformation parameter. These parameter surfaces are interpolated over the region so that we have a continuous parameter surface for each of them over the region. So if we were going to simulate rainfall at a single point, we'd simulate rainfall from this distribution. If it fell above the truncation line in the wet region, it would be rainfall. It would be transformed using our transform and given a rainfall amount. If it fell below, it would be truncated as a dry day. In terms of simulating persistence, there's also a lag 1 autoregressive model moving that rainfall on in time. So when it comes to simulating our field in space, we also have a spatial correlation function. So you simulate your spatial rainfall field, much as we did before. You then truncate all those values below 0 and transform them to give them the correct rainfall amounts and skewness in space. Our parameters vary seasonally to give us that nice Adelaide seasonal rainfall pattern. So our case study is on Coringa catchment, which is our major water supply catchment. The studies relied on 73 years of good, high quality observed daily rainfall, and there are 19 calibration sites within the grid. So in terms of what's simulated today, it's 100 realizations on a grid of just under a kilometre squared. So in that simulation, you can see it's made up of a bit over 2,000 grids, and we're doing a pretty good job of capturing the spatiotemporal statistics of our rain field evolving in time. So because of the high dimensionality of the problem, a lot of sites, a lot of seasons, a full grid, it needs some way to summarise the data in terms of performance. So what we've done in terms of presentation today is something that's good and it's been given a traffic light of green. It's statistically indistinguishable from the observed because we have less than 10% of the data outside the limits. Sites or months designated as fair, given a traffic light of yellow. Either there's more than 10% of data outside the 90% limits, but they're within 3 standard deviations, or the simulated mean and the observed mean are within 5% of one another. And otherwise, they're designated red and poor. So if we look at a quick example where we have the simulated statistic on the x-axis and the observed statistic on the y, with perfect agreement being on the one-to-one line. In this first case, we have good agreement between the observed and the simulated. So the blue represents the 90% limits. Falling on the one-to-one line means that we have good green performance. Fair, where the pink lies between, and or where the simulated mean and the observed mean are within 5% of one another, given by this dashed green line, or otherwise poor, lying outside both those conditions. So in terms of performance over a range of sites and months, this is aggregated as a bar chart using that same traffic light colour scheme. So initially we verified the model structure at the daily level. So we had good agreement between the simulated number of wet days each month and the observed. So each blue line, the 90% limits for each month and each site. Similarly good performance for the amount of rain that fell on the wet days and for the variability of each of those wet day amounts. Looking at it in terms of the temporal performance and the persistence of the rainfall, we did well in terms of simulating the distribution of wet spell lengths. So here's an example of a drier March month and the month of July for Blair. As you can see, we have good performance throughout most wet spell lengths, and the performance was similarly good over all sites for wet month groups and dry month groups. Also good for dry spells. We then looked at monthly totals, and there was similarly good performance in terms of mean, standard deviation and indicator of the lower tail and the upper tail. And when we looked at annual totals, we had good performance in terms of simulating means. However, we were somewhat under-predicting the annual variability of the rainfall in terms of annual totals, and this has mainly come out in terms of predicting wetter years that should be dry, but not really in terms of the upper tail, so we're still getting good performance for those wetter years. We did well in terms of preserving the month-to-month and the yearly correlations, and we had good performance in simulating our intensity, frequency, duration relationship, which is our relationship in terms of rainfall extremes, which is a very good test as it's an emergent property of the model and we haven't calibrated to it. Cross-validation over all the sites also shows good performance. So this table compares where we used all the data for calibration, and this as we dropped out each site individually. So yes, there is some degradation in performance, but we're still getting a lot of good performance there. Moving to the spatial performance, we looked at the number of jointly wet sites in terms of the relative frequency the model predicted, and we're doing pretty well for isolated rain, patchy rain and widespread rain, which is good because it's reproducing those behaviours across the board. And we also managed to preserve the spatial rainfall gradient, comparing the average annual total rainfall at each site. So in terms of the model, its advantages are that it's simple and flexible. You can have as many realisations as you want, and it's continuous in time. In terms of next steps, we'll move on to improve interannual variability, perhaps address the assumption of a stationary climate throughout the model, use radar data to better inform our spatial correlation structure, and move to other locations which have varied weather, so for example tropical weather systems, and look at it conditioned on a variety of other data sources. Thank you.
Good time, Bree. Thanks. We've got time for a few questions. If we have any, if you want to raise your hand. Yes, we got one. Gary?
I just wondered about information and maybe having people in the community be able to provide you with rain measures of different types for confirmation over a more diverse area.
So having more spatial data to validate against would always be of use in terms of getting our spatial correlation function better over our catchment. So that's always, more data is always more useful.
So put an article in the paper and invite people.
Graham?
I was just wondering how many parameters you've got in your model that I count as 3 each month by 12 months, 36, is that right? Or?
So 3 each month. So the 36 plus the parameters involved in the lag one auto-regressive parameters, so that's over the whole surface, so that's another one for each month, and then the interpolation itself. Yes.
Any more questions?